For this lesson, we'll talk about how to encode a cyclic code with a shift register circuit. Okay? Suppose you have a generator polynomial. Of a cyclic code. Like this. So gx equal to 1 plus x cubed. Okay. Now notice the degree of generator polynomial. Okay. The degree is 3. This means that you have a memory unit. Three memory unit. Okay. So what you do, okay, is that you draw the memory unit first. We have 3 memory unit like this. If you have taken the digital circuit lesson, okay, you will know that this is a flip-flop, okay, like a D flip-flop. Each of them can contain 1 bit. Okay. But in this class, okay, what happens is that you look at the degree of the term in the generator polynomial. Okay. If the first term, this one is x to the 0, okay, this one is x to the 1. And x cubed, okay. The left hand side here, we start with the x to the 0, okay. X to the 1, x squared, and x cubed position. Okay. If you have the number 1 here, okay, what happens is that you have to have a line here, okay, in the circuit. And if you have x1, x to the 1, so you have another line here. X squared, you don't have the term, so you don't have this line, okay? So no line here. And you have x cubed, so you have this term. Okay, so you must have a line here. Okay? Now, if you have, okay, in the circuit, okay, from the D flip-flop or the memory unit, you always have to have like, it's a shift register circuit, right? So it's shift from this one to this one to this one. So they always have an arrow coming out. If you have 2 arrows coming, okay, from the top and from the left, then you have to have an operator, right, to combine it. And this operator is called XOR. Okay, this one is an XOR operation or exclusive OR. Exclusive OR. So this one combine together and get into the second unit. Okay. This one, there's nothing from the top, right? So it's just go directly into this box. Now, this one is a little bit tricky. Okay, let me delete this first. Okay. For this, okay? What happens is that you have the data coming in here. Okay, so the data coming in here, so this one coming in, this one coming in, so this one has to go out. So you have a feedback here. And now you have the register circuit already for this generator polynomial. Okay, so it's done. Thank you. We look at another example of the encoding circuit. Suppose you have a generator polynomial like this, long one. 1 plus x to the 4th plus x to the 6th plus x to the 7th plus x to the 8. Okay, again, we look at the degree of the generator polynomial. The degree is 8, so you have 8 memory units, right? What happens is that you draw an 8 blocks of the flip-flop. 3, 4, 5, 6, 7, 8. Okay. So term here, the left hand side, the leftmost, okay, is an x to the 0, okay, x to the 1, x squared, x cubed, until x to the 8 here. So you have this term, okay, you don't have x to the 1, you don't have, okay, x squared, you don't have, x cubed, you don't have, you have x to the x fourth, okay. You don't have x to the 5th, you have x to the 7th. So you have the line here, you have x to the 6, x to the 7 here, and x to the 8. Okay. So this one, you don't have anything coming from the top. So you just go shift directly into this box. This one, you have something from the top and something from the left coming out. So you combine it and you get, okay, an arrow coming out here. This one again is an XOR operator. Okay. This one directly going out. This one you have, okay, an XOR here. This one you also have an XOR here. This one, okay, again I tell you that this one has the data coming in. So you must have an arrow here coming in. This is data. So you have an arrow coming out. So the circuit is done for this generator polynomial for a cyclic code. Thank you. For this lesson, we'll look at the encoding techniques for a cyclic code. Okay, this one will use a 7/4 cyclic code with a generator polynomial like this, and the message coming in will be 1110. This one you see that it's 7/4, so 4 bits is the number of the data bits. Okay, so we have 4 bits here, and the 7 bit is the total number of bits. So we have, this is the check bits, okay, 3 check bits plus 4 data bits. So 3 plus 4 is equal to 7. So this is correct. Now let's look at the encoding circuit. I already draw the encoding circuit for this generator polynomial. Okay, the message coming in here is this M. Okay. You can look at it as a vector because there's like 4 bits. Okay. First, you initialize the shift register circuit without all 0. So inside of the memory unit, they are all 0. And then when you shift this one coming in, okay, you will notice that 1 coming here, okay. When you shift, which means that you have a clock tick, right? And then everything coming out of the memory unit of the D flip-flop. Okay, so this one, 0 coming out, 1 plus 0 is 1. Okay, coming out here. So this one come here and come here. So what you have got is this. This one get a 1 in. This one is 0. Okay, 0 plus 1 is 1. Okay, 0 coming out will become 0. Okay, so when this bit already shipped in, what happened is that inside of the memory unit will become 110. Then this one coming in. Okay, so you have 1 coming here again. Inside is 0, so 1 coming in. Inside 0 is 1 plus 0 is 1, so you should get 1 and 1 coming out. Okay, this one you get inside the memory. Okay, this is inside the memory at this time. So this one will come out. This one will come out over here. So 1 plus 1 here becomes 0. This one is inside the unit here. So this one coming out, this one becomes 1. So you have, after this, the second bit chip in, these are what inside the circuit. Okay. Then the next one, this one coming in, but what is coming out here is 1. This one coming out. So 1 plus 1, okay? This is an exclusive OR operation or the modulo to addition, which is like this. This is the operation. Same is 0, different is 1. Okay? So same, okay? 1 plus 1 here becomes 0. Okay? In this class, in this modulo to addition. Okay, so 0 over here, 0 getting in, you got 0 here. This one coming out a 1, right? 1 plus 0, you got a 1 here. 0 coming out, you got a 0 here. So this one coming in, you got the 0, 1, 0 inside of the circuit. Then the last bit, okay, 0 coming in. 0 coming in. You got this one coming out, so 0 plus 0 is 0, okay? So this one becomes 0, 0. This one, you got 0. Getting in here, 0. 0 plus 0 is 0. 1, okay? Get over here is 1. So when the last bit comes in, you got 0, 0, 1. This is the check bits. Okay, these are the check bits, and then you can get the code word. After you got the check bits from the chip register circuit like this, notice that this one, okay, from the x to the 0, right? So this one is the least significant bit from the circuit. Okay, from this side, this one is the most significant bit from the circuit. Okay. Now, to get the code word, okay, the code word equal to this one must be the most significant bit, and this one is the least significant bit. And it starts with the message first. This one is the most significant bit. How do I know that this is the most significant bit? The most significant bit is the one that comes in first. You always input the most significant bit of the data into the circuit first. Okay, so this one must be the most significant bit. So I write it like this. Okay, so this comes from data. And then the check bits, okay, have to be flipped so that the most significant bit is on the left and the least significant bit is on the right. So this one becomes like this. And now you get the code word for this data. And you should try for yourself, changing the data into something else, maybe 0, 1, 1, 0, 0, 0, 1, 1, something like that. Okay, so 4 bits, anything, and then do it yourself, okay? And see the code word that you get, then you can compare it with the other techniques. Okay, like the binary division. Okay, to get the polynomial division to get the check bits, okay? All three methods have to get the same results.